What if I told you, right now the universe is shaking? Ripples from the most violent events since the Big Bang are passing through your body this very moment, racing at the speed of light. For a century, it was only a prediction. Einstein's idea? Tiny tremors in the fabric of space-time, so faint he believed we would never detect them. He was wrong. The universe is not silent. It echoes with cosmic collisions. It whispers with dying stars. It roars with black holes merging in the dark. And at last, we learned how to listen. This is the story of the machine that felt the universe tremble, proving a century-old theory and unlocking the hidden sounds of the cosmos. Our story begins with Albert Einstein. The year is 1916. Fresh from publishing his general theory of relativity, he made a bold new prediction. Space-time, he said, is not a static stage. It's a living, flexible fabric. And like any fabric, it can ripple. When massive objects move, when stars or black holes accelerate, they carve waves into space-time itself, ripples racing outward in every direction at the speed of light. Einstein called them gravitational waves. The most violent events in the cosmos would create the strongest signals. Supernovas exploding, neutron stars colliding, black holes spiraling together in the dark. But here's the twist. Einstein himself wasn't sure they were real. He ran the math and saw by the time these waves reached Earth, after millions or billions of light years, they would be vanishingly small. For decades, physicists argued, were gravitational waves a real force of nature or just a ghost in the equations? In 1936, Einstein even submitted a paper claiming they didn't exist, but a flaw was found. His own calculations betrayed him. The prediction survived, the hunt for the waves had only just begun. So, how small is unbelievably small? By the time a gravitational wave from a distant cosmic event reaches Earth, it stretches a detector miles long, by a distance thousands of times smaller than the nucleus of an atom. Think about that. It's like measuring a change in the distance between Earth and the Sun, smaller than the width of a single human hair. Every vibration on Earth is stronger. A truck rumbling down the road, a tree falling in a forest, waves crashing on the shore, even the hum of your refrigerator. All of it trillions of times more powerful than the signal we're trying to catch. For almost a century, it seemed impossible. A footnote in Einstein's grand theory, something we would never prove. How do you build an instrument sensitive enough to feel a tremor that faint and separate it from the constant noise of our world? It demanded precision at the very edge of physics, an idea so bold it sounded insane. And yet, in the second half of the 20th century, three scientists, Rainier Weiss, Kip Thorne, and Barry Barish, chose to build it anyway. The solution was as bold as it was brilliant. The Laser Interferometer Gravitational Wave Observatory, LIGO. Born from the minds at MIT and Caltech, LIGO isn't just one observatory, it's two, separated by thousands of kilometers, one in Louisiana, the other in Washington. That distance is everything. A true gravitational wave will touch them both at slightly different times. A local tremor, like an earthquake, won't. Each site is a colossal L-shaped machine, two perfectly straight vacuum tunnels, each 4 kilometers long. A single laser beam is split in two, half racing down one arm, half down the other. At the ends, mirrors of near-perfect precision send the beams back. In a still universe, they cancel each other out. Perfect silence. But when a gravitational wave passes, the silence shatters. One arm stretches, the other compresses. Suddenly, the beams no longer return together. For a fleeting instant, a flicker of light appears. That flicker is the signal. That flicker is the universe, trembling. And for this vision, this triumph, Weiss, Thorne, and Barish were awarded the Nobel Prize in Physics in 2017. After decades of planning, building, and refining, advanced LIGO was finally ready. And then, before its first official science run even began, it happened. At 9:51 UTC on September 14, 2015, a signal arrived. Clean, powerful, simultaneous in both the Hanford and Livingston detectors. It began as a faint rumble. Then, in less than 0.2 of a second, it surged upward in frequency and intensity before cutting off, instantly. When scientists transformed that signal into sound, it was a single, unmistakable chirp. That chirp was the echo of a cosmic catastrophe, two black holes colliding. For billions of years, these giants, one 29 times the mass of our sun, the other 36, had been locked in a gravitational death spiral. In their final heartbeat, they whipped around each other at nearly the speed of light, tearing space-time itself and unleashing unimaginable energy. Then, impact. They merged. And in that instant, a single black hole of 62 solar masses was born. The missing three suns weren't gone, they had been annihilated, converted directly into raw energy, just as Einstein predicted, E equals mc squared. That energy rippled outward as the most powerful gravitational waves ever detected, a flash brighter than all the stars in the visible universe combined. And after traveling 1.3 billion years through the cosmos, that final whisper of the collision brushed past Earth. It was recorded. It was named GW150914. The 100-year search was over. Einstein was right. Detecting GW150914 wasn't just about proving a theory, it was the birth of an entirely new way of seeing the universe. For all of human history, we studied the cosmos with light. Visible light, radio waves, X-rays, but light gets blocked. It scatters, it's absorbed. And many of the universe's wildest events, like black holes merging, emit no light at all. They are, by their nature, invisible. Gravitational waves are different. They aren't light. They are vibrations in the very fabric of reality itself. They travel through space almost completely untouched, carrying pure, undistorted information about where they came from. It's the difference between seeing a lightning strike and hearing the thunder. For the first time, we could hear the universe. Suddenly, we had a tool to study the unseeable. We could directly measure the properties of colliding black holes, their mass, their spin, their distance. We confirmed pairs of stellar mass black holes really do exist, and they merge. Since that first discovery, the LIGO Virgo Kagra network, an international collaboration including the Virgo detector in Italy and Kagra in Japan, has recorded hundreds of these events. By March 2025, the collaboration had logged over 200 candidate detections in its fourth observing run, bringing the total number of gravitational wave events to nearly 300 since 2015. Today, detections are no longer rare. They've become almost routine. And this marks the rise of a new field, multi-messenger astronomy. For the first time, we can combine what light tells us with what gravitational waves reveal. Together, they give us a complete picture of cosmic events. We're no longer just looking at the universe, we're listening to its symphony. So what's next? With every new observing run, the detectors become more sensitive, able to hear fainter, more distant rumbles across the cosmos. The current run is scheduled to continue until November 2025, promising even more discoveries. But the most exciting part isn't just about finding what we expect, it's about discovering what we don't. What if we detect waves that don't match the signature of colliding black holes or neutron stars? Some theories suggest other, more exotic objects could be out there. Could we be witnessing the crash of hypothetical boson stars? Could a hidden signal reveal evidence of a wormhole, a theoretical tunnel through space-time itself? It's speculative, yes, but gravitational waves remain our best chance to test these wild, frontier-shaping ideas. And scientists are listening for something else, a faint, ever-present background hum of gravitational waves, echoes from the dawn of time. Primordial waves forged in the first instant after the Big Bang. They would carry secrets of the universe's birth, an age no light-based telescope can ever touch. Finding them would be like hearing the echo of creation itself. We are standing at the very frontier of the unknown. From a mathematical curiosity in 1916 to an almost daily cosmic forecast in 2025, the journey to detect gravitational waves has completely revolutionized how we see the cosmos. We've built machines that can feel the most delicate tremors in space-time, and in doing so, we gave ourselves a brand new sense to explore the universe. We've learned that space isn't empty or silent. It's a dynamic, roaring ocean of energy. The cataclysms of the past are constantly rippling through our present, carrying the secrets of black holes, the stories of dying stars, and maybe, one day, the very first sounds from the dawn of time. Every ripple is a message from the universe. The question is, are we ready to decode them all? If you want to keep exploring the hidden universe and the biggest questions in science, make sure to subscribe and ring that notification bell. Thanks for watching.